the robot pulled it off quite well, and the model running this was RT2X, which is a cross-embodied VLA model. Notably, it was trained by Quan Vong, who had never actually worked with this robot before himself, and my student Kevin Black, who was overseeing the experiment at Berkeley, said it's unstoppable. Now, of course, Kevin had been working on these kinds of robotic tasks for quite a while, so perhaps the significance of this to us seemed much larger than it does to the rest of the world. But I do think that there is something to this that suggests a different way of thinking about robotics that's much more in line with recent advances in large-scale foundation models. Okay, so what are these kinds of models? The first vision language action model was a model called RT2 that was developed a couple of years back. And the design of this VLA model was actually very simple. It basically paralleled vision language models, multimodal LLMs that take in language and images, and just adapted it to robotic control. So the way that we would train a VLM is we would take data that contains images and text, and we would train them for things like question answering or captioning. And to enable such a model to control a robot, we simply take robotic examples, basically images that the robot has seen, as well as ground truth actions in a demonstration, and frame them essentially as question answering examples, where the answer consists of the numerical representation of the robot's action. And the original RT2 model simply used an existing vision language model design without any modification and only changed the data to enable it to control robots. And the reason this is significant is because now you can take all of this knowledge embedded in the multimodal LLM, all of the semantic knowledge, all of the understanding of the visual world, of complex problem solving and so on, and transfer that knowledge into the robotic domain using examples of robotic control. Now, of course, to get foundation models to work, we need more than just the right model architecture. We also need to think about data. And the other thing that happened also a couple of years back was the advent of diverse cross-embodiment robotic datasets. So the first serious cross-institutional effort to build something like this was the RTX project, which took data from 34 different research labs, about 22 different kinds of robots, lots of different skills, and try to put it all together into a kind of a web-scale training set for robotic learning to use with these kinds of new VLA models. Now, I could tell you about lots of statistics in RTX, but maybe it's easier to just show you some videos just to give you a sense for how different these different robotic scenes were. So these are just a handful of examples of different platforms sourced from labs all around the world. These are not, serious practical tasks. These are kind of academic tasks, so the robots are not doing terribly useful things, but it is very diverse. And one of the really exciting things that happened when we took this cross-embodiment data set and combined it with VLA models is we saw, I think really for the first time, that general-purpose robotic models could outperform more specialist models in the domains that the specialists were designed for. This is really what we get so excited about with foundation models in other domains. Like, the reason LLMs are so exciting is that you can have a more general model that is better at specialized tasks like machine translation and text summarization than prior methods that have been designed specifically for those domains. And this is not something that had actually been seen in robotics before. So the way that we tested this is we asked a few of the labs that had donated their data to take the model that was trained on this combined data set and test it on whatever task that they were doing research on. And these videos show some of those evaluation tasks. You can see they're pretty different: routing cables, opening drawers, manipulating furniture, things like that. Again, kind of academic quality tasks, not the tasks of the greatest practical importance, but very varied. Here are the results. The rightmost rainbow-colored bar shows the cross-embodiment RT2X model. And the leftmost bar in each group is whatever specialized method that lab had been developing for their own tasks. And it's a different method for different labs. The middle bar is a baseline. So what makes this so interesting is that the generalized model, as you can see in the averages on the far right, was about 50% better across all these different labs than whatever model that lab had been building for their specific domain. And I think this is showing the beginnings of that kind of blessing of generality that we've seen with foundation models in other areas. So that really got us thinking that perhaps the era of robotic foundation models really is almost upon us. Now, of course, it's not all perfectly solved. If we actually look at the kind of tasks that these systems are doing, well, it's kind of cool that they can follow language, but truth be told, these are fairly rudimentary things. It's like, move the apple between the can and the orange. This is not the task of great economic importance, of great societal significance. It's almost more like a little self-contained intelligence test for the robot. The diverse data really helps. This robot was actually the one that was most overrepresented in the data set, and even then, including data from other robots boosted its generalization performance on the hardest language following examples by 3x. So it was 3 times better at the hardest language following examples than a baseline that used only data from this robot. But again, the tasks are pretty rudimentary. So what I'm going to talk about for the rest of this presentation is how we can go from these early vision language action models that essentially directly adapted the classic VLM design and just shoehorned robotic examples into it as almost like a numerical visual question answering problem, to a more modern VLA design that is suitable for complex, dexterous, and highly fluent robotic manipulation. And to tell you about this, I'll first tell you how we go from language models to vision language models to vision language action models. So I'm sure all of you are familiar with how LLMs work. They are transformers that use self-attention to predict future tokens in text. So this is the formula that we're all hopefully very familiar with. And if you want to get a language model like this to also be able to process images, what you have to do is take images and embed them into the same embedding space as the language tokens. So typically this is done by taking something like a vision transformer as an image encoder that tokenizes the image and then uses some kind of projection to embed those tokens into the same space as the embeddings of language tokens so that the LLM can make sense of them. And then you train this thing to predict text given a text and image prefix. So what I would call first generation VLAs essentially used exactly this architecture. They just replaced the suffix. Instead of making it be a natural language description of what's going on, the suffix was the numerical representation of the command that the robot should issue. In fact, the first VLA literally used ASCII representations of numbers for this. But this is pretty primitive because you're discretizing the actions very coarsely, you're using a lot of tokens, and you're kind of neglecting a lot of the continuous structure in robotic trajectories. So to go beyond this recipe for something that can accommodate much more complex robotic control, what we can do is think about the analogy to VLMs. What VLMs do is they almost add like a little visual cortex to the LLM backbone, represented by that image encoder. So what we can do for more sophisticated VLAs is add a little motor cortex, a separate machine whose job it is to look at the representations inside the LLM and produce smooth, continuous, and dexterous actions. And that's basically the design for what I would call second generation VLAs, which are the most widely used architecture today. There are a few different ways of doing it, but roughly speaking, they all add some additional component, either an action decoder or a separate expert in a mixture of experts style design that is typically not trained with cross entropy. It's typically trained with something more suitable for continuous actions like diffusion or flow matching. And basically its job is to process all the continuous information. So to use an incredibly naive analogy, if you think of the language models like the prefrontal cortex, the VIT as the visual cortex, this is the little motor cortex, and it gets to look into the representations inside the LLM, but has its own job to do, which is to produce these continuous actions. So second generation VLAs add a dedicated continuous output mechanism that can specialize for motor control, and this is really powerful because now you can do much more sophisticated tasks much more fluently. So what I'll tell you about as an example of a model in this category is the Pi0 model. The Pi0 model was developed about a year ago at Physical Intelligence, uses this kind of second generation VLA recipe together with a pre-training and post-training kind of design that in some ways parallels what is done with foundation models in language and vision. So the Pi0 model was pre-trained on about 10,000 hours of data from many different robotic platforms, and then it can be adapted to fairly intricate tasks. Like, for example, we can adapt it by post-training on high-quality data of folding laundry. The high-quality data alone isn't enough to really solve the task reliably, but if you combine it with pre-training on very diverse data, then whenever the robot makes a mistake and encounters some unfamiliar state, that pre-training phase has already taught it how to handle all these diverse situations. It can fold various different clothing items. It can even do that with different robots. It's far from perfect, so it'll often make mistakes. You can see in the lower right corner, it takes a few attempts to grasp that object. But because it has that pre-training phase to acquire a lot of knowledge about physical interactions, it can often correct its mistakes when it makes them. Here are a few more examples of perturbations and recoveries. We didn't really expect this to happen. It was kind of an emergent behavior, but if you put a second laundry item, the robot will kind of struggle with it for a little while, but eventually it figures out that that second item really gets in the way and just puts it back. So that's pretty neat. We were pretty impressed with this, so we decided to mess with it some more. So here you can see Michael putting different objects in front of the robot, messing with it, and it keeps kind of soldiering on. And this looks pretty natural, I think, to a lot of us, because this is what we'd expect a person to do, but as a roboticist who's been working on this for a long time, I was actually very surprised to see this stuff just sort of happen without any particularly deep additional kind of algorithmic insight, just by leveraging large data sets and the right kind of pre-training, post-training formula. Now, since then, we've made quite a bit of progress, especially towards more long horizon and complex tasks. About half a year back, we released the PyO5 model, which is kind of the next increment on our VLA. What PyO5 adds beyond this addition of the action expert is a reasoning mechanism for longer horizon tasks. So in this video, you can see the PyO5 model cleaning up a bedroom. Interestingly, this is a bedroom in a house that the model was never trained in. So it's actually generalizing to an entirely new house, and it's figuring out how to put away the laundry, make the bed, and all these things. And to enable it to do something this complex with so many different stages, the model actually incorporates an internal reasoning mechanism where it's issued a high-level command like clean the bedroom, decides internally in language that the next stage for that command is to pick up the pillow, generates that text, and then based on that text generates the action. So it has this additional chain of thought reasoning step built into it. One of the interesting things we found when we added this mechanism is that now we actually also had access to an additional source of supervision. We found that after a while, the motor control in the model was actually pretty good, and we could improve it further simply by talking to it, without actually giving it any additional action supervision. So we call these verbal instructions, where if you put the robot in a new home and it doesn't succeed, you can walk it through the task in words, basically coach it to say, like, in this kitchen, if you want to clean it up, first pick up that plate over there, then put it in the sink. Okay, now you got that? Okay, now close the microwave. And you can add that as training, and the model actually gets better simply from adding this additional language supervision to training. So this is a video of this in action just to make it more concrete. You can see in the top left, the human is providing it a textual description of what it should do next, walking it through the task, in this case for how to dry the dishes. And that's really exciting because that means that now these robotic models can actually get better simply from having people talk to them without even requiring this additional expert teleoperation for getting the action commands. Obviously not for all tasks, you need to be in a domain where you already have the repertoire of motor skills, but the point here is by building on these vision language backbones, you can unlock other sources of supervision for a task that would otherwise be very hard to do. The other interesting thing, and this is coming back to the question of data sets, is that for the PyO5 model, all of these experiments that I showed with controlling mobile robots actually used a data set that had relatively little data from mobile robots themselves. So obviously, as we do this work, we collect all of the data from all of the robots we've ever used, and you can see a brief overview of it here. Only 3% of the final data set actually consisted of data from mobile robots. The rest came from other kinds of robotic platforms in other domains, static robots, single arms, dual arms, etc. And what this is showing is that we are in fact getting that generalization across different platforms that is making it easier to bootstrap a new application. And here you can see more videos of different tasks that PyO5 was able to do in various test environments. The last thing I wanted to mention about PyO5 is how generalization changes with the number of training environments. So because we wanted this model to generalize to entirely new homes, we tested it when trained on different numbers of training homes. And we actually found that after about 100 training homes, the performance matched what we would get if we actually trained directly in the test environment. Now, it's not perfect, so there's still a ways to go, but for this kind of approach, the generalization aspect of it, at least, is actually doing pretty well. Interestingly, if we don't use pre-training on all these diverse different platforms, then performance is much worse, even if we train on the test environment. And of course, if we don't train on the test environment, if we use the same training set, performance is pretty terrible in the test case. So to wrap up, a few takeaways. What we have so far is a prototype of a generalist model trained on many robots, a VLA recipe that is suitable for dexterity and fluent robotic control, and pretty good performance across a range of complex tasks. And it's a model that can improve from instruction rather than just action. But there's still a lot left to do. These models are still trained with imitation. They're not optimized for task success, robustness, or speed. And there's a lot more room for sophisticated planning, thinking, and generalization. And of course, since this is the PyTorch conference, if you want to try the code, it is there. We originally wrote it in JAX, but we have a PyTorch port now. And the PyTorch port actually works, so you're welcome to try it out. Both Py0 and PyO5 are available there. Thank you very much.